In this video we're going to return to Laplace transforms, and since the previous one we talked about the theory, in this video we're going to talk about some examples. We're going to work through, I don't remember how many, 3 or 4 different examples of applying Laplace transforms to ordinary differential equations, and we're going to assume that you have already figured out the differential equation representing your system. We're going to work our way through the Laplace transform and show how we use these. So as a reminder, what we talked about in the previous video was that in our previous classes we have gone directly from differential equations to a solution. And remember, a solution is the time domain response y of t, which describes the output variable. Assuming that x is your input or u is your input and y is your output, if you can find y of t, that is the solution of the differential equation. And this is the way that we did it in your diffie class. We went directly across, we found the homogeneous and the particular portions, we added them up. And what I told you before was this is hard. And it may not be hard, it may just be tedious, but there's a better way to do things, at least for the purposes of this class. For other classes it may be different, but for this class we're going to go through Laplace transforms so that we can write everything as algebraic equations. And those algebraic equations let us find cap y of s, that is going to be our solution in S domain. And then we can do an inverse Laplace transform to get back to the solution in the time domain. And this is going to be easy. And we like easy. Easy makes things easy. So let's look at a first order system. This is a standard first order system. It's got our time constant tau. So tau times y dot plus y is equal to 0. And we have an initial condition. So let's start by taking the Laplace transform of both sides. So on the left we're going to get tau. It's a constant. We'll pull it out and then we'll just do the Laplace transform of the y dot. So Laplace transform of y dot is going to be s y of s minus y of 0. Now let's do the Laplace transform of y, and that's just going to be y of s, and we'll set that equal to 0. So if we pull that y of the cap y of s, put them together, we get tau s plus 1 quantity times y of s. And let's move that y0, and we know that it's, we can substitute it in a value of y naught, so we'll get a tau y naught on the right hand side. And we can divide both sides by the tau s of 1 plus 1, sorry. So we get y of s is tau y naught over tau s plus 1. And so if you go to your tables, you can look up this form and you'll see that we actually need to put it in terms of y naught over s plus 1 by tau. And so when we apply our inverse Laplace, we can say y of t is y naught e negative t by tau. That's straight off the tables. So there it is. That is the solution to this differential equation with 0 input and initial condition y of 0 is y naught. So what if we have the case on the right where we have, instead of a 0 input and an initial condition, let's have a 0 initial condition and an input. Same idea. We'll find the Laplace transform. So again, tau, pull that out, s y of s minus y naught plus cap y of s is equal to, and the Laplace transform of k is a constant times 1. Well, the Laplace transform of 1 is going to be 1 over s. So in this case, I know that that y of 0 is going to be 0. So I can get tau s plus 1 quantity times y of s is equal to k over s. So let's divide both sides again by the tau s plus 1. So we get y of s is equal to k over s tau s plus 1. So this one is not exactly in your tables. You're going to have to perform a partial fraction expansion. So we can say y of s is going to be equal to some a over s plus some b over s plus 1 by tau. And notice I put it in the s plus 1 by tau because that's going to be what's in your table rather than tau s plus 1. And so if I go through that with my tables, what I'm going to find is that after simplification it's going to be k times 1 minus e to the negative t by tau. So there we go. That's y of t, sorry. So that's our solution. So if this is a step response with an initial condition, that is to say, we've got both these cases merged together, we've got an input and we've got an initial condition, well, this is what we call superposition. It's a linear system, because that's what we're dealing with in this class, is linear systems. Then the response should be the superposition of the response with the input and the response with the initial condition, which is to say, I can just add them up. I can say y of t is going to be k 1 minus e to the negative t by tau plus the component due to the initial condition, and my initial condition here is 5, so 5e to the negative t by tau. There we go. That is the response to both the input and the initial condition. So let's look at another one. This is the free response, which is to say that there is no input. The right-hand side of the equation is 0, and we have initial conditions. And in this case, we're going to get two distinct real roots. So if we do our Laplace transform of our differential equation here again, we're going to get, let's do the y dot term, s squared y of s minus s y of 0 minus y dot of 0 plus 9 s y of s minus y of 0 plus 18 y of s is equal to 0. So let's pull out all the y of s portion there. So that's going to be s squared plus 9s plus 18. And you'll notice that that exactly matches the coefficients of the ODE, which is no surprise. And that on the right-hand side, we'll get the initial condition term. So we're going to get an s y of 0 plus y dot of 0 plus y of 0. And we know that that is all going to be equal to, well, the y of 0 terms are going to go to 0, and the y dot term is going to go to 3, so the only thing left is going to be 3. So I can say y of s is equal to 3 over s squared plus 9s plus 18. And certainly I can factor out that denominator, and so I'll get 3 over s plus 3 times s plus 6. So there's my two real roots, a negative 3 and a negative 6. Excuse me. So they're distinct in that they're different. They're real because they're not complex. And I can perform a partial fraction expansion. So there's going to be some a over s plus 3 plus some b over s plus 6. So if I solve for a and b, they'll come out to be 1 and negative 1, but you can check that. Then my solution is going to be y of t is equal to a e to the negative 3t plus b e to the negative 6t. How did I get that? I took it off the tables. I took the s plus 3 part from the table, the s plus 6 part from the table, and since I can perform the partial fraction expansion to get them into these sum of terms, then I can just do each one individually because, again, it's a linear operator. So that is the free response. We'll get into the forced response later, but let's start with let's go and do instead the free response of a second-order system with identical real roots. So a very similar case. In this case, we could assume that it's a boxcar running into a boxcar arrestor, which is a way to slow it down. And so it might be governed by this differential equation, so we can do the Laplace transform again. So s squared y of s minus s y of 0 minus y dot plus 10 s y of s minus y 0 plus 25 y of s is equal to 0. Excuse me. Pull out the y of s terms. S squared plus 10s plus 25 times y of s. And let's move our initial conditions to the right-hand side. So we're going to get an s y0 plus, y dot of 0 plus a 10 y of 0. And so if I put in my values for my initial conditions, that's going to come out to s plus 15. And I can divide both sides by that chunk on the left. So y of s is going to be s plus 15 over s squared plus 10s plus 25. And if you factor that denominator, you're going to get an s plus 5 and an s plus 5. So s plus 15 over s plus 5 squared, which, if we're going to do partial fraction expansion here, because this is a repeated root, we're still going to get our s plus 5 in the one term, but we need a second term, and that's going to be our s plus 5 squared. So because it's a repeated root, we're going to have one that's by itself and one that's squared. Look it up in your tables. You'll see that it's very similar again. So we're going to get, if you solve for a and b, you should get 1 and 10. So we're going to get a e to the negative 5t, which is just like what we'd expect normally, plus, and now our b term, we're going to get t e to the negative 5t. And that's off our tables. That's because we've got a squared term there. But what if I didn't want to calculate out a and b each time? What if I wanted to get it the easy way? Well, fortunately, MATLAB can do that for you using the residue command. The residue command is going to take as inputs the coefficients of that ratio of s polynomials. So, in the previous case, we had, let me flip back in my notes here and get it written down correctly. We had y of s is equal to 3 over s squared plus 9s plus 18. And in this case, we had y of s is equal to s plus 15 over s squared plus 10s plus 25. So if we take the coefficients of the terms here, we get a 3 in the numerator for the first one, so that goes in our first spot here in the oh, I lost the technical term, but we're going to put it in the parentheses there. And we'll take a 1 from that s squared and the 9 and the 18, and we'll put them into a vector. That's again a matrix with only one row or one column. In this case, it's a row. Put that into the second spot there. We can do the same thing in the next example. We get a 1 and a 15. Put them into our vector. That's our first operator there, and we get a 1, a 10, and a 25. Again, into our vector, put it in there. And so the residue command operates on these, and it figures out what should those poles be, the roots of the denominator. And so the roots of the denominator are here in the p-values. And the other question is, what should those coefficients a and b come out to be? And that's going to be r, the residues. So if you look at the previous case, we said a over s plus 3. So s plus 3 means that the root there is going to be a minus 3. And b over s plus 6, which means the root is going to be a minus 6. And I told you that if you calculate it out, a equals 1 and b equals negative 1. Well, there you go, 1 and negative 1. Same case here. They're both at negative 5. One of them is going to be a 1 and the other is going to be a 10. So there's an easy way to calculate out those coefficients. MATLAB is great for this sort of thing. Here's another case that's probably a bit more likely that you're going to see, is what happens if you get complex roots. So if we do this again, just like before, I'm going to skip the steps. You can work them out. You should get s squared plus 6s plus 25, which is what we always expect, times y of s. And on the right-hand side, we're going to have our initial conditions, and when you solve those out, you're going to get s plus 3. So y of s is equal to s plus 3 over s squared plus 6s plus 25. Now, if we complete the square, go back and check your math textbook on completing the square, we'll get s plus 3 over s plus 3 squared. And the thing that's left over then is going to be 4 squared. And so if you go and you look at your table, you're going to see this one on your table. And so we are going to get a transform then of e to the negative 3t, and that's off your table again, times cosine of 4t. And this is a very common form. We've got, in this case, a decaying sine or cosine. you can see when you see this, if the initial conditions don't line up to such a clean case, you'll have to come up with some portion that's going to transform into sine and some form that's going to transform into cos. But in both cases, what you're going to see is it's going to be a make sure I draw the cosine correctly. There we go. It's going to be something like this, where it's a standard cosine, but it decays at an exponential rate. And this is what's typically seen with a characteristic. Roots are complex. If you need to do it by hand, again, remember you need to complete the square. Always complete the square. So here's that same sort of case, but now we've got an input and no initial conditions. So this is a step response. This is not a step response. Well, this is an input case instead of being a free response. So s squared again plus 6s plus 25 all times y of s. And if I also take the Laplace transform on the right-hand side, I should get an s plus 25 u of s. That's a terrible u. There we go. That's a better u. Oh, here it is. I'm telling you that it's a unit step response. I just didn't write it down here in my notes. And what that means is that u of s is going to be a unit step 1 over s. So let's just substitute that in. So y of s is going to be s plus 25 over s squared plus 6s plus 25. And I'm going to multiply that by u of s. But u of s is just 1 over s. And so if I split this up for partial fraction expansion, I'm going to get an a over s term plus a b over s squared plus 6s plus 25. Now I left it like this again because I know that it's got complex roots. And so if you prefer, I could write it as s plus 3 quantity squared plus 4 squared. But I think you can see that I can't factor that anymore, so that's as reduced as it can be. And so if I do my inverse Laplace here, I get y of t is going to be equal to 1. A is going to come out to 1 in this case. And b is going to come out such that I need to split it into cosine and sine terms. And so when I do that, I'm going to get minus e to the negative 3t cosine 4t minus 1/2 e to the negative 3t sine 4t. So this is a very common case that we have to have both a cosine and a sine. And so if you check your tables, you're going to see that the difference between the two is going to be in the numerator. So if you get a particular case where you get an s in the numerator, we're going to have to work out a split to get this right. Let's look at another case very similar. In this case, again, it's a unit step, so we're going to say u of s is equal to 1 over s. So I can do the same sort of thing. I can say that before I do that, I'm going to get y of s is going to be equal to s plus 3 over s squared plus 6s plus 8. Notice that I can do this a little faster because I've got no initial conditions. I can ignore the initial conditions. I can just go straight to pulling out the coefficients. And that's going to be multiplied by u of s, but I know u of s is going to be a 1 over s. So when I write this out, I'm going to get an a over s plus a b over s plus 2 plus a c over s plus 4. And this is because I factored the denominator. I split it into an s plus 2 and an s plus 4, and I separated them out. And so I can use either residues command or I can solve for a, b, and c. But when I do my inverse Laplace, I'm going to get a plus b e to the negative 2t plus c e to the negative 4t. So there we go. That's how we do these sorts of things. If we want to look at a more complicated example, consider a vibration absorber, something like this. In this case, I'm going to just tell you that we're going to assume 0 initial conditions. And I've got some ODEs here. You could solve for these if you really wanted, but they're already prepped for you. And in this case, I know that the input is the force which is causing it to vibrate. And in this case, the output is Z2, the upper mass. I want to know that the upper mass is relatively small motion for this whole thing. So this could be like a shock absorber system. So if I want to do this, I can start by taking Laplace transforms of both of these. So I could say m1 s squared plus b1 plus b2 s plus k1 plus k2 quantity z1 of s minus b2 s z2 of s minus k2 z2 of s is equal to f of s. And I can do the same thing for the second one there. I can say m2 s squared plus b2 s plus k2, all of that times z2 of s. Let's say a minus b2 s plus k2 quantity z1 of s is equal to 0. So there's my two equations. I've Laplace transformed both of them, and surely I can look at this second one and I can say, well, z2 is going to be equal to, I'm going to move the z1 to the right-hand side. So it's going to be b2s plus k2 over m2 s squared plus b2s plus k2 times z1 of s. And so that'll allow me to make a substitution into the previous one. So let me skip ahead here to the next slide so I've got some more room to write. And so if I substitute that in for z1, I should get m1 s squared plus b1 plus b2 quantity s plus k1 all times m2 s squared plus b2 s plus k2 over b2 s plus k2 times z2 s minus the chunk that was originally multiplied by z2, b2 s plus k2 z2 of s is equal to f of s. And so now by making that substitution, I've got this all in terms of f of s, my input, and z2 of s, my output. So I can just go ahead and rewrite it. I can combine those two pieces together, I can find a common denominator, and then I can rearrange this such that I'm going to get z2 of s is going to be equal to b2s plus k2 over, and this is sort of a monster equation here, m1 s squared plus b1 plus b2 s plus k1 plus k2 multiplied by m2 s squared plus b2 s plus k2 minus b2 s plus k2, all of that multiplied by f of s. Oops, I missed a squared here. b2 s plus k2 squared. All of that multiplied by f of s. And there we go. We've got what we're going to call a transfer function between f of s and z2 of s. Well, I suppose actually if I want to make it a transfer function, I need to divide to the other side, put f of s there. So there's just my transfer function. So if I take this big chunk on the right, my transfer function, and I multiply by some known f of s, then I hope you see that I can take that monstrosity there, I can perform a partial fraction expansion, I can inverse Laplace it, and I can get a solution for z2 of s, the motion of the upper mass, as a function of time based on my knowledge of the input as a function of time. And that'll be easier than trying to go through and solve the homogeneous parts and the particular parts. Now, it's easier because in this case I did algebra instead of having to do messy differential equation calculus in the other case. So this is how we're going to solve things in the future. You need to know what the input is, and you need to be able to convert to Laplace, do the algebra, and then convert back. So there we go. There's some examples of Laplace transforms, and we will pick this up with transfer functions next time.